Hello physics students. So in the last couple videos, we really revised our understanding of gravitation. I'd like to begin today by just summarizing some of the things that we've learned. The first thing is that the force of gravity is not actually a constant with altitude. If you move over a large enough distance on a global scale, you would begin to notice that the force of gravity gets weaker the further you get from the surface of the Earth. We can actually calculate the exact number of newtons using that equation we learned, which is on the reference table, Fg equals capital G m1 m2 divided by r squared. So gravity gets weaker. The other thing we learned is that the force of gravity direction also changes. So for example, for an object here, force of gravity points this way. An object over here, the force of gravity points this way. Right? So it changes the direction for horizontal displacements. Two very important ideas. We also learned that the gravitational field, little g, is not a constant 9.8 as we assumed it was up until this point in the year. In fact, it also gets weaker the further you get away from the Earth. We could calculate the exact value with the formula little g equals capital G mass of the planet over r squared. And little g, also the direction changes as you move around the Earth. These important facts lead to some radically different motions. In the next couple videos, we're going to be studying the motion in the gravitational field and the gravitational force that vary according to how we learned with those patterns. The first such motion we're going to study today, objects that are in circular orbits, what I call forever projectiles. So suppose we've got planet Earth and we put a big cannon on Earth. Maybe it's at the North Pole, or it could be maybe we're looking down at the North Pole and this is on the equator. It doesn't matter. Somewhere on the Earth we've got this huge cannon up on a big tower. The cannonball fires the cannon fires the cannonball. And the first cannonball, we don't load the cannon much with gunpowder, so it lands somewhere over here, and it lands after time 1. The next cannonball, we fire with more propellant, more gunpowder, so it ends up shooting out of the cannon at a faster velocity. Now, in the last part of gravitation, we said that that projectile should land at the same time. The velocity has no bearing on the falling, so whatever it takes to land, fast shot, slow shot, land at the same time. But now we can see that is not true. This dotted line would show a flat surface, and you can see that when cannonball B now gets to that dotted line, it still has not touched the Earth. It has more to fall. So it actually takes longer to fall. Time 2, this one lands in time 2, which is longer than time 1 because of the Earth's curvature. Okay? And I could shoot even faster, projectile C, maybe if this is like, in South America, maybe this lands in Japan or something like that, right? So we could start getting really far on the global scale. And then let's suppose I shoot even faster. Something very special can happen. This projectile comes out of the cannon like this. Now, before I continue, let me ask you, would you say that projectile is falling? Is it accelerating? And the answer is, you better say yes. If it wasn't falling, if it wasn't accelerating, it would go in a straight line path, according to the path of no force, according to Newton's first law. So it's accelerating, it curves. And it still hasn't touched the Earth, so it continues to fall. Keeps falling, keeps falling, keeps falling. And I'm standing by the cannonball looking like this. Where's the cannonball? Why isn't it landing? And I'm looking like this, looking out like this. And then the cannonball hits me in the back of the head. Can you imagine that? And you're waiting, and then it comes around, hits you. Well, maybe I'm smart enough. So I duck, and then it misses my head, and then it repeats the motion. Repeats the motion. over and over and over. It never lands! Exclamation point. It falls forever. But it never gets any close to the ground because the Earth is round. Okay, so that's the fascinating thing that can happen because the Earth is round. You can have things falling forever. A lot of people look up at the moon and they say, hey, you're a physics teacher. What keeps the moon up? How come it doesn't fall and crash into the Earth? Nothing keeps it up. It's falling, falling, falling forever. But it never gets close to the Earth because the Earth is round, right? So there again, I could say, hey, you asked me that question. What a silly question. Let you in on a news flash. The Earth is round, right? If it were flat, it would fall and have something have to keep it up. But it falls continuously, never hits because the Earth is round. Fascinating, fascinating, fascinating. All right, so we're going to do some analysis with that. But first, what I want to do is create a pause so you could copy this down if you need to. And then the next thing I want to do is talk about something else called apparent weightlessness. See, a lot of people, they see the videos of astronauts in space stations and they see them like this floating. They say, oh, there's no gravity up there. They're weightless because it's like they're floating above the floor and they never fall and crash into the floor. And that is not correct, okay? In order for them to be truly weightless, we learned earlier, way back in the first unit, that weight is the same thing as saying the force of gravity. If they're weightless up there, there's no force of gravity. And the International Space Station, where the astronauts currently are, where there's astronauts up there doing studies, is about 205 miles, I think is what I saw when I looked it up, which converted is about 330,000 meters above the surface of the Earth. On the global scale, if you do a ratio and compare that to this globe, the space station is about 2 centimeters from the surface of this globe on this scale. And it's going around like this, okay, in a circular path, as we mentioned. That is not far enough away for the force of gravity to be zero. We'd have to be way, way out. Maybe beyond Pluto, then there's no more force of gravity. Here there's still force of gravity, and in fact we could calculate that. For a person that weighs 1,000 newtons on the surface of the Earth, if they were up in the space station, do G m1 m2 over r squared, and you would find that they're 903 newtons. They only lost 10% of their weight. They still have 90% of their weight up there. And yet why are they floating? Why does it look like there's no weight? The reason why is that if they were truly weightless, they would go in a straight line like this path if they were weightless. They're not! Exclamation point. What happens is they fall towards the Earth because there's a force of gravity, therefore there's an acceleration. They accelerate, they fall. Now if the space station was held up and then they fall, they would fall and hit the floor. But the space station is not held up. As the person falls, the station falls the same distance as the person. Person falls 1 meter, station falls 1 meter. So the person never reaches the floor. The illusion is that they are weightless. It's an illusion. They're falling, same as the ship is falling, and it looks like they're never falling down, but they're constantly falling down together. Okay? An analogy would be this. Suppose you're in an elevator, Empire State Building, 100 floors or whatever it is. You jump off the floor, and at the moment you reach your peak, someone cuts the elevator cable. What would happen in that case? Well, let's see. Maybe I'll grab this box here. So this is an old box lid. What would happen is, if the elevator cable wasn't cut, you'd fall and hit the floor. But what happens is you fall 1 meter, floor falls 1 meter. You fall 2 meters, floor falls 2 meters. You fall together, and then you're saying, hey, look at me floating above the floor, right? And of course, when it hits the ground, and then you hit the floor, then you realize, oh, I was falling the whole time. It was an illusion, okay? Same thing up there. So what I want you to do is just jot this down for a moment, and we'll copy it into your notes before we move on. All right, now, the next thing we're going to do is we're going to calculate the speed of objects in orbit at the altitude of the space station. How fast must they be going to maintain this orbit. So, calculating speed of orbit of satellite, I made up a mass. It's not the space station. Suppose it's a satellite that's like for communication of cell phones or something like that. It's got a 1,200 kilogram mass and it's at this altitude above the Earth's surface. So the first thing, I drew a diagram. The altitude is here, drawn at a scale. You know, it's really closer, but I wanted you to be able to see that the radius of orbit has to be calculated as the radius of the Earth, capital R, plus the altitude of orbit, which is what this is saying right here. So this is the radius of the Earth, this is the altitude given. There, I punched that on a calculator. Once again, the radius of the Earth, in these calculations, you have to be able to find the radius of the Earth. So, here's the front cover of the reference table. And right here, we see mean radius of the Earth, 6.37 times 10 to the 6. So you have to find that in problems and utilize it in a calculation. So there it is. Now, here's the big idea. The physics idea, the main thinking, all the concepts are right here. This thing is in circular motion, just like we studied earlier in the year. I don't care if it's a satellite around the Earth, a hunter caveman spinning a rock over his head on the end of a sling, a roller coaster going around. I don't care what it is. If it's in circular motion, you need a centripetal force. That can come from anything. A string, friction, normal force. Any force can make circular motion and can be the centripetal force for that situation. But for the satellite, there's only one force up there. It's in outer space. Nothing touching it. It's the force of gravity of planet Earth keeping that thing in circular motion. Kind of like, almost like a string when you're whipping it around. This equation does not say there are two forces that are equal and balanced out, and then this doesn't fall because it's in equilibrium. It's saying we need a force to accelerate, a centripetal force to go in circular motion, and this is the one force on the object that provides it. No equilibrium, okay? Constant acceleration, circular motion. Then I go to the reference table and I fill in these pieces. What is the centripetal force? What is the force of gravity? So you need to be able to find these, as always, as I've mentioned. So let's have a look here. Reference table again. I scroll up and basically near the bottom here, I have F centripetal is ma centripetal, and a centripetal is v squared over r. So what I can do is right where it says a, I can put in v squared over r and get mv squared over r, the centripetal force equation. Going back a little bit, I find the force of gravity formula right here, g m1 m2 over r squared. Okay, so those are, here's the centripetal force equation, here's the gravity equation. Now notice I've changed this a little bit around. Instead of m1 and m2, I put capital M for the Earth because it's big. That's what I like to do. And I put subscript E. So that's, instead of M1, ME, mass of the Earth. And instead of M2, I put MS, mass of the satellite. So it's clear for me. I could see really what's going on. And this is not the mass of the Earth. The Earth isn't going around the satellite. The satellite's going around the Earth. So that's what's in circular motion. That's what goes there. Now, what we have to do is plug in all the numbers. So let me make some room. I'm going to need a lot of room here because the numbers get big. All right, so let me create a pause to allow you to catch up if you need to. All right, let's now plug in all these numbers. The satellite was 1,200 kilograms. So right here, 1,200 kgs. V squared is what I'm looking for. The radius of orbit I figured out is 6.7 times 10 to the 6th. On the other side, I've got capital G. All right, I won't make you dizzy. Front cover of the reference table, the very top number, it's there. So 6.67 times 10 to the minus 11th. And we need those units. Don't forget the units. Otherwise, you lose points on the Regents. Now we need the mass of planet Earth. So we got mv squared r g, mass of the Earth we need. So again, front cover of the reference table. It's right here near the top of the reference table. And that's 5.98 times 10 to the 24th. And the other mass is the mass of the satellite, 1,200 kilograms. All divided by radius squared, which is right there. Now, a lot of crunching, a lot of room for error here. I recommend before you begin punching, is to look and see, because there's some things you could do to simplify. See 1,200 here and 1,200 here? We could actually get rid of that. I'll do it lightly because you want to copy that down. Also notice 6.7 10 to the 6, and then we got it here squared. So what we could do is, maybe I could do it with red. Maybe it'll distinguish it a little bit lightly. That I could cross out and cross this squared out, okay? And what's left on the left side is just v squared. And if I do this times this divided by this to the 1 power, because 1,200 is gone and the squared is gone. I did this ahead of time, so let's see. 5.95 times 10 to the 7th. Square root both sides, and I get 7,716 for the speed. Just to give you an idea, it's enormously fast. That's like over 5 miles in 1 second. So from our high school, if you shot something going, so maybe it goes across the Hudson River in 1 second, that would be fast enough to go into orbit. Okay? In miles per hour, I did a conversion. It's over 17,000 miles per hour. You don't have to write this down if you don't want to. Just to give you a sense, wow, 100 miles an hour is fast. 17,000 miles an hour? Turns out that in the beginning when I said I'd fire a cannonball off a tower and then it'd come around and hit me in the head, that would not really happen. I would have to shoot that cannonball so fast that as soon as it hit the atmosphere, the friction would cause the cannonball to vaporize. Gone. No more cannonball. That's how fast. So you need to create these orbits above the atmosphere. Otherwise, whatever you're trying to put in your orbit is just going to burn up, okay? Vaporize. That's incredibly fast. One other thing I want to do before we finish, how long does it take this thing to go around the Earth once? So what we call that is the period of orbit. So that's the next thing. Period of orbit. And what we use is the symbol capital T is the time to go around once the Earth. Whenever something repeats over and over again, we use the symbol instead of lowercase t, capital T, and that tells me, oh, it's something that occurs over and over. This goes around and around, capital, just a little thing. All right, so the way we do that from this velocity, or the speed, I should say, is we use the basic formula v equals d over t. But we're going around a circle, right, as you could see from that picture. And the distance around a circle is 2 pi r over t. And I'm going to put capital T. So I'm going to put 7,716 meters per second. 2 times pi times 6.7, the radius over there. So I can multiply this t to the other side and then multiply all this together, which gives me 4.21 times 10 to the 7th. Divide by this 7,000, and I guess I have to do it here. T equals, what was it? 5,456. And, you know, you're probably thinking, what's 5,000 seconds? Sounds like a lot. Well, it's about 1.5 hours. So let me create a pause to allow you to copy all this down. All right, so interesting, those people, those scientists in the International Space Station, if they're looking down at New York, they go around about, you know, in 1 hour they come back to New York. They saw, oh, New York is over here, okay. They saw, you know, Africa, China, Pacific, and then New York again in 1.5 hours. Kind of cool to imagine what that'd be like to keep passing over the Earth like that. All right, so that's a kind of calculation you might have to do. I want to point out something, though, in the homework, that there's a problem where you have to do this in reverse. In other words, what they tell you is the time that it takes something to go around. Like the problem is you're watching something in a telescope in another galaxy or another solar system somewhere else, and you're watching some moon go around a planet, and you could time how long it takes to go around once in the telescope. You could also, from kind of astronomy techniques, figure out the radius of orbit of that moon around that particular planet. Or maybe it's a planet around a star. So from the time and the radius, you could figure out the speed, right? You got radius, you got time, boom, 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 you get speed, and maybe you calculated this. Then what you could do is here, when you plug in numbers, what would happen is the v would now be a known number. It'd be whatever you calculated from this step. But what would be the unknown is the mass of the planet or whatever it is that the thing is orbiting. So very often you could solve backwards and get the mass, well, we know the mass of the Earth, but you could get the mass of something else doing this calculation in reverse. Fascinating stuff, how you can look through a telescope and figure out the mass of a planet, and you never went there. You're just looking at it in a telescope. All possible with these orbit calculations. Really cool stuff. All right, so that's our first study of motion, projectile motion, not for a flat Earth, but for a round Earth. And what we see, because of the curvature, the nature of the force of gravity, and how it changes, is this possibility of creating a projectile that goes around in a circle and never lands, constantly accelerating forever. We calculated the speed, we calculated the time of orbit. One more thing I just thought of. You don't even need the mass of the satellite. If it's not given to you, we could have canceled it right here. Boom, boom. And I could have said, there's a satellite. How fast is it going? And the mass of the satellite dropped out, and you would be able to calculate it anyways, even if the mass of the satellite was not given. All right, well, I hope you enjoyed the video. I'll see you in the next physics video.